Today I present a new cutting-edge data analysis tool that we've been working on, which gives us greater insight into deformation trends on the Earth's surface. This technology is making critical data more accessible to project teams across the organization. With this new technology, we take information analysis into our own hands, enhancing our ability to make informed judgments. In the context of geotechnical monitoring, imagine being able to predict the failure of a dam even a few days earlier than would be possible using conventional monitoring methods. Think of how that could change the outcome of such a failure in terms of environmental destruction and loss of human life. As an organization centered on technical services, this is an important advancement in a technology that is changing what we know about Earth movements and what we are able to deliver to our clients. We've been using technology to observe, explore, and interpret the world around us for centuries, but now we're seeing technology advance faster than ever before. With this comes an enormous amount of information, and in this information overload lies the inherent challenge of sifting through and extracting the right data to make informed critical decisions. However, with the new data processing and visualization techniques we've been working on with the Geospatial Innovation Office, we're unlocking more power now than ever before. Interferometric synthetic aperture radar, or INSAR, is a remote sensing technology that is revolutionizing what we know about how human activity is impacting the Earth and its climate. INSAR uses satellite-based technology to map the surface of the Earth every 12 days, providing so much data it results in datasets with millions and even hundreds of millions of data points. As the surface of the Earth shifts over time, the satellites pick up these movements and we can begin to compare the successive images to monitor deformations. INSAR deformation data has a diverse range of applications and uses. It can be used for measuring ground movements on tunneling projects, in urban developments, dams, and mine sites, to inform real estate transactions, to measure sediment deposition and shoreline erosion, and to understand the effects of losing permafrost in northern areas, as Jim McKinley discussed in his presentation last week. The Earth is mapped in pixels, ranging from as large as 20 meters by 20 meters to as small as 3 meters by 3 meters. As we manipulate the surface of the Earth by loading it, unloading it, dewatering it, or flooding it, we can measure with this technology how the Earth deforms as a result of the conditions we impose. A color scale is used to identify movement either toward or away from the satellite, with hot colors indicating movement away, meaning subsidence, and cool colors indicating movement toward or heave or uplift. Here we see the impact of a dewatering effort in an urban area, with subsidence shown in red. This example is applicable to areas all over the world. As we draw more and more water out of the Earth to supply our cities, agriculture, and industry, we are impacting the Earth's surface. In this particular example, INSAR technology helps us to understand how the Earth's surface is affected by water usage. Stantec, like many other companies, buys INSAR data from vendors. The problem is, until now, we've been relying on the vendors' interpretations of the displacement data, and we haven't had the tools to verify or interpret it ourselves. This is a major concern because we make decisions regarding the stability and safety of Earth structures based on this data. When we have insufficient data or are unable to scrutinize the data effectively, huge failures can result, failures that might otherwise have been prevented. This is where the INSAR analytics tool we're developing comes into play. An example of an issue with vendor interpretation came up in an INSAR analysis we completed as part of our dam monitoring systems. We observed in the data set what appeared to be a subsidence event occurring on one of the dams. Then we found the same subsidence signature at other locations as well, in parking lots, urban areas, and other areas of the site. However, it was determined that a randomized error pixel had caused a shift in the entire data set, making it appear as if subsidence was occurring when nothing was happening at all. This example illustrates how important site-specific knowledge and precise data verification is to every project we work on. Decisions to stop construction, buttress a structure, or evacuate nearby populations must be based on accurate and reliable information. The image we're looking at on this slide is of a mountainous area near a reservoir and power generation station. Highlighted in yellow is an area of slope stability or landslide. The client developed a monitoring system using in-ground instruments approximately 10 years ago, but the instruments soon sheared off due to increasing movements and monitoring stopped. How often do we find ourselves in that situation? Our recent INSAR analysis enabled us to identify a critical issue, that the slope is still moving at a constant rate and mitigations must be planned to prevent the ongoing movement from affecting the penstock pipelines. The image on this slide here shows an INSAR analysis from a nearshore marine environment. Stantec completed an INSAR analysis so our scientists could understand shoreline erosion and sediment deposition. Natural processes have resulted in impacts to the fisheries in the area, including oyster farming. Using INSAR technology has allowed for greater efficiency in collecting information and more insight into what's happening as a result of sedimentation. Can you imagine collecting this information with boots on the ground? We're decreasing the effort required to get the information we need while increasing our accuracy and coverage at the same time. We've developed automated processes and simplified workflows in the INSAR analytics tool, which provide a means to transform raw data from any of our trusted vendors into data sets that can be queried by any of our clients and staff. Data is input into our calculator where it is transformed into a data set that can be used in Esri ArcGIS software. Exports are configured to view vertical movements, east-west movements, and more importantly, to create heat maps that can be configured over different time periods. These heat maps give us the visual clues we need to understand what is happening on the Earth's surface. The heat map images we produce indicate the magnitude and direction of Earth movement. Pixels within the analysis area can be selected by the user and averaged to understand the displacement time relationship of that area of interest. The displacements can be graphed as an average or as individual pixels. We're also working on statistical tools for the data so we can increase our confidence in our interpretation and sift outliers from the data set. Here are several applications we've built in GIS to help one of our clients collect and manage field data. We're working to integrate INSAR data analysis and interpretation into existing monitoring and surveillance workflows and to digitize this in the ArcGIS environment. This will bring all our spatial data together so we can put the information we're working with into clearer context. These are new and exciting developments that differentiate our INSAR analytics tool from the visualization platforms that we have previously been relying on. Here's a side-by-side heat map image of an identical study area shown over 2 time periods of interest. The highlighted area shows a slope beneath a dam. Through INSAR analysis, we have determined that the slope movement has been accelerating year over year since 2016. This information has changed the client's focus on prioritizing earthworks in the area. Through INSAR analyses, we found that structures are behaving in ways we've never imagined. For instance, we have evidence now that earth and water dams expand and contract seasonally with filling and emptying, inhaling and expanding with spring freshet as the reservoir rises, and exhaling and contracting with falling water levels throughout the summer. These behaviors have never been witnessed before. It's a bit like the National Geographic Adventures, where Sir David Attenborough thrills with excitement at witnessing a never-filmed event or behavior in the animal kingdom. With these technological advancements, we can experience the same thrill in the world of engineering.